Hey Honors Chemers, welcome to the Neutralization and Titration podcast with Ms. Heaton. We're going to go through the basics of neutralization reactions and how they are applied to titrations, which is a process that we use in chemistry. So far in this unit we've talked about pretty much just acids and bases separately. However, we've started talking about what happens when we combine them in terms of common ion effect and buffer solutions. Well, today we're going to talk about adding acids and bases in an amount that cancel each other out, and we call that neutralization. So when an acid combines with a base, a neutralization reaction has occurred. And we can write this chemically in terms of an equation where an acid reacts with a base. They will always make water and some sort of salt. By salt, we don't mean sodium chloride. We mean any ionic compound, as we've talked about in class. So here are the reactions that we're going to practice on. And yes, that naming stuff you learned is important, so let's give it a shot. Nitric acid is HNO3, and it will react with potassium hydroxide, which is a strong base, to make water. So we have the OH and the H coming together to make water. So we'll call that HOH. And what's left? Let's see, we have K plus and NO3 minus. They each have a charge of 1, so they'll cancel each other out. It'll just be KNO3. And we can rewrite the water as H2O. So that would be the neutralization reaction that occurs between those two. Let's try another one. Hydrochloric acid is another strong acid, HCl. And calcium hydroxide is a strong base. Now remember that calcium has a charge of +2, so we're going to need 2 hydroxides to react with that. And like we said, they always will react to make water, HOH, and a salt. In this place it'll be calcium +2 and chlorine with a -1. Okay, now we're going to have to crisscross here because they have different charges, so it'll be CaCl2. And now we're going to need to balance the equation. So hopefully you remember how to do this. I would start maybe with the chlorines. There's 2 here, so we'll need 2 on the other side. We also have 2 hydroxides here, so we'll need to put a 2 here. So 2 H's are from here, 2 hydroxides are from the calcium hydroxide, so there's our balanced equation. Now notice that we need, that each calcium hydroxide has twice as much base as the acid does. So amount-wise, we need to add twice as much hydrogen chloride, hydrochloric acid, as we do base. Now, we could do stoichiometry every time we wanted to do a neutralization calculation, but there is an easier way, and that's to use normality. You see here at the bottom that normality is just the molarity multiplied by the number of acid or base ions that are in the formula. And this just makes it a little bit easier when we do neutralization calculations. Let's try a few examples of this. Here's 4 examples that we're going to do. If we have 1.5 molar sulfuric acid, there are 2 acid protons there, so we'll need to double the concentration, so we'll end up with a 3.0 normal solution of our acid. The next one, hydrochloric acid. There is only 1 acidic hydrogen there, so the normality and molarity happen to be the same. For the next one, calcium hydroxide. Calcium hydroxide is CaOH2, so that means that there are 2 base units in each calcium hydroxide, so we'll have to double the concentration. So that'll be 5.0 normal of base. And phosphoric acid, try this one on your own. Phosphoric acid is H3PO4. So there's 3 acidic hydrogens, so we'll need to triple the molarity to get 4.5 normal of acid. Great. So now we're going to use those in some calculations. There is an equation for neutralization because at the neutralization point you have equal moles of hydrogen and equal moles of hydroxide. So that reaction is happening in the correct stoichiometric ratio. And like I said, you could go back and do the stoichiometry, but it is a lot easier if you use normality. Now remember this equation, N1V1 equals N2V2. This worked for dilutions because you had equal moles at the beginning, 1, and at the end, 2. Now we can replace this with normality of the acid, because we need to have equal moles of acid and equal moles of base at our neutralization point. So that's our new equation. And here's an example. How much 1.5 molar sodium hydroxide is required to neutralize 100 milliliters of 2.5 molar hydrochloric acid? Okay, first thing you want to look at is the normality. Sodium hydroxide only has one OH, so this would just be 1.5 normal solution. Hydrochloric acid only has one acidic hydrogen, so this would also be 2.5 normal. No multiplication needed here. So we can just plug this into our equation, Na times Va. Our acid, we have 2.5 normal of hydrochloric, and the volume is 100 milliliters. And that's going to equal the normality of the base, which is 1.5, times the volume of the base, which is what we're looking for. So 2.5 times 100, that is 250, divided by 1.5. Let's calculate that real quick. Y'all have your calculators, right? You're doing this, you're not just watching me. Okay, so that's 167 milliliters. However, we need 2 sig figs, which would be 170 milliliters of base, sodium hydroxide. So there's our neutralization answer. We would need 170 milliliters to neutralize it. Great. Okay, let's try another one. How much 3 molar aluminum hydroxide, that's AlOH3. So let's go ahead and find the normality there. There's 3 hydroxides, and it's 3 molarity, so 3 times 3 is 9. So that's 9 normal of our base. How much is needed to neutralize 200 mils of 1 molar hydrobromic, that's HBr? So that's just going to be 1 normal of our acid. Okay, still using the equation, Na times Va equals Nb times Vb. Our acid we have 200 milliliters of, and its normality is 1. That's going to equal the normality of our base, which was 9, times the volume of the base, which we're solving for. So divide both sides by 9, and the volume of the base will turn out to be 200 divided by 9. That's about 22 milliliters. Whatever units your volume is in at the beginning, it will be at the end. Oh, and we should probably put the chemical on there. That would be of aluminum hydroxide. Great. Why don't you try one on your own? So hit the pause button, give this one a shot, and rejoin me when you think you got it. Okay. Here's the next one. We've got phosphoric acid, so it's 2 molar H3PO4, which if we find the normality will be 6 normal, because there's 3 hydrogens. So that's our acid. And we want to neutralize 200 milliliters of 2 molar calcium hydroxide, CaOH2. So that will be 4 normal of our base. So we plug it into our equation. Normality of our acid, which is 6, times the volume of our acid equals the normality of the base times the volume of the base. So 4 times 200, that's 800, divided by 6. The volume of our acid will be 133 milliliters, though with sig figs, that would need to be rounded to 130 milliliters of phosphoric acid. Great. Okay, folks, we got one more thing we need to talk about. How would we use this in the lab? Well, the way we would do it is with a process called a titration. And you've actually done one of these with our last unit. A titration is the controlled addition and measurement of the amount of a solution of known concentration required to neutralize a measured amount of solution of unknown concentration. So usually we know maybe what our acid's concentration is, and we want to know what the base's concentration is. So we'll slowly, drop by drop, out of a burette, add one of our chemicals to a certain amount of our unknown chemical, and figure out exactly what volume we need of the known molarity and what volume we have of our unknown molarity, and use our N1V1 equals N2V2 equation to solve for that. Or we could look at it graphically, because the graph will show us the equivalence point. The equivalence point is kind of like the neutralization point, the point at which you have equal amounts of H plus and OH minus. And your graph could look a lot of different ways, depending on what kind of acid and what kind of base you're using. So if you have a strong acid and a strong base, the equivalence point will be right here. Well, in all of them, the equivalence point is where the pH changes rapidly. It goes from being very basic to being very acidic. So if it's strong and strong, your pH will be about 7 at the equivalence point. If you have a strong acid but a weak base, at the equivalence point your pH is going to be more acidic, so it'll be below 7. If you have a strong base and a weak acid, your pH at the equivalence point is going to end up being a little bit above 7, more basic. And if you have weak and weak, well, it really depends on what the Ka and Kb are, but it might end up being close to 7. And it's really hard to do a titration curve for those because it's difficult to see exactly where that rapid change in pH is. So another way to look at the equivalence point is with an indicator. An indicator is just a chemical whose color changes depending on what the pH is. You may have used litmus paper in middle school or maybe in an earlier science class. Litmus paper has a blue color above 7 and a red color below 7. Another chemical option is methyl orange, which changes color around pH of 5, it looks like. And phenolphthalein, which is the one we use most commonly, changes pH right around 8. So right as you turn basic, it turns pink. And so this is actually one that we'll use a lot because its endpoint changes color at the equivalence point for a strong acid and strong base. And that's what we want to happen. We want to choose an indicator whose color changes right when our equivalence point occurs. So if you're doing a strong and strong, like strong acid, strong base titration, and your pH curve, your titration curves look something like this, the equivalence point would be right here. And phenolphthalein would be a good choice if you are slowly adding base, because bam, as soon as you get right above 7, it'll turn pink and you know that you are at your equivalence point. Okay, so we will get to practice this tomorrow in class. Please send me an email or send your teacher an email if you have any questions. Thanks, folks.